at some point from like the department seminar I gave. So if you don't like
Maybe
this
we'll be-
recording, the other one probably has separate audio too. So if, I don't know, my audio quality right now isn't that good, the other version should be better. Yeah.
I see. I'm just gonna deport it. Okay, so hello everyone. So today we will have like Alex Lewandowski. He's a PhD student supervised by Dale Schumann and Marlos Makito at the University of Alberta. His interest is understanding the scalable continual learning algorithms with the goal of developing algorithms capable of learning autonomously. So today he will give us a talk on learning continually by spectral regularizations. So yeah, the floor is yours.
Thanks for that introduction, Tung. Yeah, so I'll be talking today about learning continually by spectral regularization. If you have questions throughout the talk, feel free to chime in. I can answer them as we go. The talk will be mostly high level. So if you have a high level question, that's great. If you'd like to know more details, maybe I'll address them as they come up, but I can always discuss the lower level details later in the talk too. So before I go into the details of what I'm going to be talking about, spectral regularization, I thought I'd go over a little example demonstrating the problem of continual learning. I'm going to do so through this history of nice. So it turns out the meaning of this word nice has changed a lot over time. So consider the problem that some ancient alien AI faces, where it hears the phrase, my supervisor is nice. And so in the 1200s, the word nice meant foolish. And so when it heard it for this first time, it figured out from context, my supervisor is nice means my supervisor is foolish. And so it ingested that word, learned its meaning, and used it, throughout the day. Time goes on from the 1200s to the 1300s. The meaning of this word actually changes. It's no longer the meaning is no longer foolish, it is timid. And so when it hears this new phrase, my supervisor is nice, now, instead of thinking my supervisor is foolish, it needs to distinguish between, is my supervisor foolish or is my supervisor timid? This distribution shift from the 1200s to 1300s is okay. The ancient alien AI is smart. It picks up this new meaning for the word nice, but time goes on again. And then in the 1400s, now there's a new meaning for this word nice. Now it means delicate. And at this point, maybe the alien AI is getting a little tired of all these changes to the word's meaning. So it might have decided to forget the word foolish, or the meaning of the word nice as foolish, or decides not to use it anymore. Time still goes on, and in the 1500s to the 1600s, now it means careful. And at this point, it's getting very tired of all these changes, and it decides from now on, I'm only going to be using the word in the context of careful. Time goes on again. In 1700s, it actually means agreeable, but at this point, the AI is finished. It doesn't want to learn anything new about the word nice. It's tired of all the changing meanings. From now on, it's only going to be using the term in the context of careful. And then finally, in the 1800s, it's like the more present definition in terms of kind. And at this point, maybe the alien AI just short circuits and forgets every single version of the word nice, and also refuses to learn any new version of that word. And so this is not really desirable for a continual learning algorithm. Continual learning means, you learn forever, you continue to learn. And so what we want at a minimum from the system is for it to be able to adapt to these changes. If it forgets things here and there, that's fine. At the very least, we would want it to be able to pick up on new definitions. So that's the topic of this talk. And what we propose is a method called spectral regularization for continually training neural networks and continual supervised learning. And so I'm going to go over slightly more formally this notion of learning continually and discuss the notion of plasticity and trainability. Then I'll motivate our method spectral regularization in terms of understanding what trainability means at initialization and how can we sustain those properties. And then finally, I'll talk about represent some continual supervised learning experiments. Okay. So plasticity and trainability. You may have heard this term plasticity in the context of continual learning. It's been picked up a lot in the last couple of years. Recall the definition of continual learning that I intuited from the example about the ancient alien AI. It's about sustaining your ability to learn. As you see new contexts for a word or as definitions change, you can pick up on these new definitions and use them. So this paper by Shabansh Doher on continual backprop kind of introduced the idea of neural networks losing plasticity over time. And they define this idea of plasticity as the ability to keep learning from new data. Learning usually means generalization, right? Like you see some contexts, some examples, and some labels, let's say like an MNIST. You don't just memorize all the examples, right? You learn something. You're able to generalize to data that you haven't seen before. So when we think of learning from new data, what we really mean is like understanding, or the agent is able to identify like the underlying concepts of the data, generalized to new examples. But we can think of something slightly simpler. Instead of plasticity and learning, we can think about trainability and optimization. So I changed a couple words here from plasticity to trainability. And the definition for trainability is the ability to keep training from new data. So the distinction might seem subtle, but really training is about optimization. Like how well can you bring your training error down? Like, can you reach a local minimum? And I'll note that like training is necessary, but not necessarily sufficient for learning. So if you're able to generalize from certain examples to certain examples, that must mean you're able to, at least fit the examples that you've seen before in your training set. And so if you weren't able to even do that, you probably won't be able to generalize. So you will need to be able to be trainable to learn something. And so before we can think of continual learning, we should ask ourselves, can we be continually trainable? Yes, Tom.
Yeah, so I'm just wonder like, so in order for us to learn, like you have to be able to train, right? So that's the whole like things here. It's not like it's like that's why it's a necessary condition, but it's not sufficient because you also have to generalize as well. Is it correct?
Yeah. So usually when you see like decompositions of like risk, it's like partly optimization error, partly like generalization error. There might be certain algorithms, I guess, that can generalize well without maybe training as well. Like, of course, if you regularize, you're not training as well, but you might be generalizing better. But some degree of training is necessary. Okay, so this is what we're going to be thinking about. Instead of plasticity and learning, generalization, we're going to think about trainability and optimization. And I'm going to go through a small example with you that I like to use. We'll see maybe bigger scale experiments later in the talk, but this is the running example I like to use. So in continual learning, we have usually a data set and a non-stationarity. In this case, the non-stationarity is this label randomization, and the data set is MNIST. So what does this look like? We have MNIST observations. So these are digits collected from, I guess, like the post office, and they are represented in black and white, and there's a label associated with each of them. Usually these labels would correspond to what these digits actually mean, but in this case, they're randomized. So for example, this 7 has a label of a 2. Even though it's a 7, we're going to ask the neural network just to memorize this label. There's other depictions of the digit 7 that actually may have the correct label, 7, but others may have another label of 3, right? Every single observation in the data set is given a random label. And then we're going to ask the neural network to just train on these random labels for t iterations. And after t iterations, the task will change. What does this task mean? Well, the task is the assignment of labels to observations. So between task 1 and task 2, all these labels have changed, and we're going to ask the neural network again, train for t more iterations, memorize all the labels. This is going to keep going until, like, say, task K. And for each of these tasks, there's going to be a new randomly assigned label for each observation. And so what we're going to be asking ourselves is, if we were to train a neural network, even without any regularization, just using SGD on the sequence of tasks, can it keep memorizing labels? So on the first task, or maybe I'll explain the axes first. So on the y-axis here, I have the online accuracy. So I'm going to measure the accuracy through training. On the x-axis, I have a number of iterations. So between 0 to 40,000 iterations, there's going to be about 50 tasks. And I'm going to show you a couple tasks at a time. So the first task we're able to reach 100% training accuracy, which means we're memorizing all the labels that we see. This is expected, right? Neural networks are relatively big function approximators. They should be able to do this. And then we're going to change the task and train it again, and see that we are able to keep memorizing these labels from task 1 to task 2. But as we keep going to task 4 or task 8, this ability to memorize these labels goes down. We have this loss of trainability. And if you keep going, it just keeps getting worse. So we go from being able to fit perfectly all these training data to the point where we're getting about 50%. And I'm going to summarize all of this by just looking at the training accuracy at the end of each task, and the curve looks something like this. Initially, we're able to fit the data perfectly. Over time, we get something about like 20% accuracy. And again, we're able to do this at initialization, but we lose this ability over time. That's why it's referred to as loss of trainability. So what matters for neural network trainability? This is actually a pretty important question, like in the early stages of neural network research, maybe 2 decades ago. If you were to take a neural network and design your own AutoGrad software, you may or may not be able to get your neural network to train on some data set. But after some research on like improving architecture and initialization, the optimization landscape before all of that kind of looked like this, where this is kind of a simplified depiction of what the optimization landscape looks like. But you can imagine the height of this surface as the training loss, and the 2 spatial dimensions as like 2 particular parameters, or a projection of the high dimensional parameters into this 2-dimensional space. And so if you get initialized somewhere in these troughs, it might be very difficult to escape and find this good minimum because of the curvature of this landscape. And then, after decades of research on architecture and initialization, we have something that looks a bit more like this, where all those bumps have been smoothed out. And so it's quite easy to go from any particular initialization to the minimum, because it's essentially a quadratic and convex. Okay, so it seems like neural network trainability is important. It might be particularly important for continual learning, where we don't really have control over where we initialize at later tasks. But nevertheless, maybe we can attempt to understand trainability better at initialization, and then use that information to design better methods for continual learning. Yes.
I'm just curious, like about like the previous slides. Like, can you just like briefly explain like why you causing like a drops there, like a drops in like the accuracy there? Like, are there
You mean like here?
yeah, here, like why when you increase the number of iteration, like, and then when you reset the task, like why it's dropping? Because like
Yeah.
it's just intuition, high level intuition there.
Sure. So of course, like at initialization, like let's say you randomize your neural network parameters, your predictions on any given observation are going to be at chance. There's 10 classes, and so the chance that you'll get a particular image right is 10%, because you haven't done any training. The question is, when you go to the second task, why does it drop? Well, think about like the task being faced here, right? If you have all these labels that you've learned, like you see this image, I guess it's a 5 or something, and you've learned that it's a 1. And then if you were to the second task, well, that image is now a 2, right? So you're going to be wrong on almost all of the images, except for some images where by chance, maybe the label didn't change, because these are randomly assigned. So all the information that you learned from before is no longer correct. And that's what's leading you to be incorrect at the beginning of a new task. That's what is happening at this drop here.
I see.
All the information you learned from that previous task is useless in this context of continual learning. Not all tasks, not all problems are like this, but this one is.
I see. But then what happened like at the like a 10,000, like 100,000 iterations? Like why it's not going to like up to 1 again? Like why just like going to like I don't know, like 0.9 or something like that, and then it's go down to like 0.3, something like that.
Yeah, that's exactly the question. Why are neural networks losing trainability, or why are they losing plasticity? That's the question that we'd like to understand. It's not so simple. There's many different things that contribute to this effect. For example, you might have thought that the way I set up the problem, random labels, is kind of strange. And it's by design, actually, because MNIST without randomization of labels is actually quite simple. You can fit a linear function and almost perfectly get relatively high accuracy, like maybe something like 99% accuracy from a linear function approximator. With random labels, that's no longer true. Like the problem is more difficult to represent. Like the target function mapping particular images to random labels is just more complicated. And so because this problem was a little bit harder to learn, you see this loss of trainability quicker. If you were to do other problems, like let's say reinforcement learning, there is some evidence to suggest that like loss of trainability also happens in reinforcement learning because you do have distribution shifts. But it might be much slower because, for example, if you were to learn a value function for your initial policy, like a random policy, and then you were to update your policy, maybe the policy doesn't change that much. It's better than random, but maybe for a lot of states, you're still picking the same action. The non-stationarity isn't so severe. Whereas in this case, the non-stationarity is severe. You have to retrain on every single observation that you've seen so far. And so that's what's kind of, those are some factors that contribute to this loss of trainability, but it's not fully understood.
I see. So like just a bit spoiled. So you're saying that like the spectral regularization will improve like what is happening here, right? I think it's supposed to be like all one for all across iterations. That's it should happen, right? Not like just like decreasing over time. So that's
Yeah. If for example, we can reach 100% training accuracy and each task afterwards is roughly the same difficulty, right? Like no particular randomization of labels is really that much difficult than any other. We would expect or hope that if we can reach 100% training accuracy on the first task, then on the subsequent tasks, we can reach at least close to 100%, not without this decay.
I see. Okay, thank you.
Great questions. So I guess in an effort to understand why this phenomenon of loss of trainability occurs, let's try to understand better what happens for trainability initialization. First, I want to point out some previous work that uses initialization to sustain trainability and some quotes from these papers. So earlier I mentioned continual backprop. This is one of the more recent papers, and perhaps the first paper really to call attention to the problem of loss of trainability in like modern deep networks. And their solution is uses random features to inject, their solution is to inject random features that extend the benefits of initialization throughout learning. So there's this quote, basically. One way to extend the benefits of initialization throughout learning is by continually injecting random features. So that's exactly what I just said. There is another more recent paper that does this in a different way through regularization. So L2 regularization towards initialization is the idea from this paper. And the quote from this paper is that parameter values that are close to initialization can be recruited for rapid adaptation to a new task. The idea being that, okay, well, we don't really know how neural networks learn in the sense that, it's a high dimensional optimization landscape. It's kind of difficult to understand what exactly the optimization trajectory is doing. But if we know that the initialization is good for trainability, if we keep the neural network parameters close to initialization, then at the very least, we can reset them by regularizing towards initialization and then training again on like a new task. And this is all done through a regularizer. And so there's already a lot of work that uses the idea that initialization is important for trainability, but let's try to understand it a little bit better. And so there's some work that tries to understand this with singular values. So this is the approach that we take. And if you're not familiar, a singular value decomposition is a decomposition of a matrix. So there's this matrix that takes vectors on this circle and maps it to this ellipsoid. That's what a matrix does. It's like a linear transformation. And any matrix can be represented in terms of singular value decomposition, where you were to rotate these vectors by v star or v transpose if they're real, and then scale them by the singular values. So sigma here is a diagonal vector, diagonal matrix, and that rescales these vectors. So before, it's just a circle rotated, but now it's a scaled circle. So it's like an ellipsoid. So in this case, the sigma matrix has sigma 1 and sigma 2 in its diagonal. Everything else is 0. And then afterwards, you have another matrix that rotates this again. So any matrix can be represented this way. And there's growing evidence that actually the distribution of these singular values is quite important for training neural networks. So people have, for example, shown that at initialization, if you're to take the singular values of your weight matrices and to plot them, they obey this Marchevko-Pasteur distribution, Avichenko-Pasteur distribution. This is this MP fit. And it's not uniform, right? The values themselves of the parameter values themselves are randomly distributed, maybe according to uniform or according to Gaussian, but the distribution of the singular values are not uniform. It's just a property of random matrices. Nevertheless, there's not like that many outliers, right? Like you have a lot near 1, some near 2, but nothing like too large, right? This is at initialization, before any training. Throughout training, though, outliers do emerge. So you may have, for example, a couple outliers that are much larger than the bulk of the distribution. So you have many near 1, some near 10, and a few near 20, right? This is a heavy tail distribution because you have a couple large outliers in your singular values. And you may even have a rank collapse where the bulk here gets collapsed into something very close to 0, and you can't even see them, but you have a couple outliers that are much larger than near 0. So in this case, in either of these cases, we have large outliers, and this might be problematic for learning because we knew that initialization was important, and the initialization had this property, this distribution with singular values. Yes, Mark.
Oh yes. So I just wanted to ask. This is, if I understood correctly, you have it's easier. I have a better property for learning when I'm closer to initialization of the weights. But is this initialization just random initialization for parameters, or is this just what's the initial distribution of the weights? Is it like a set standard deviation or anything?
Yeah. So there's a couple of choices you can have to initialize parameters. I think in this plot, it's Gaussian. That's just the results that people have for like closed form distribution of singular values. So for each of your weight matrices in your neural network, you'll initialize them by sampling from a Gaussian distribution where the standard deviation might depend on like the input dimension and output dimension for that weight matrix.
Oh, got it. Thank you.
Yeah. So at initialization, we have these random values. They're singular values. The singular value of that matrix looks a bit like this. And then throughout training, of course, we only randomly initialize once at the very beginning of training, but then we learn from data through gradient descent. And that's what drives some of these values to get large. So this might be a problem. And let me just verify that in the earlier example I showed with random label MNIST, that the maximum singular value does indeed grow. Again, at initialization, we have something like 2.5. Later in training, it's something like 20. So does this happen in practice as well? So initially, we have something close to 2, less than 2, because maybe the neural network that I was using was a bit different from the paper I was citing. But over the course of training, it increases. And as we saw before, the trainability goes down while this is increasing. So maybe that's problematic. We can also see that even the minimum singular value in this case goes up, but not at the same rate. And we can actually summarize the relative distribution of these singular values by the rank. Not the exact rank, though. The exact rank counts essentially the number of 0 singular values. What we're going to show is something called the effective rank, which measures the dispersion of the singular values. What this is showing is that the effective rank is going down. And what this means is that the larger singular values are becoming larger faster than the smaller singular values. Initially, it's close to 100. Later in training, it's closer to 40. And so this might be cause for concern. And this is what we're going to be focusing on. Just to summarize the story that I painted in the last couple of slides, at initialization, we have small random values according to maybe the sub-Gaussian distribution. This leads to approximately uniform spectrum, where the spectrum is this distribution of singular values. And then over the course of training, we'll be doing continual learning. And because we keep learning things, we keep getting these outliers in the spectrum. These outliers in the spectrum contribute to low rankness of our weight matrices. And perhaps maybe this low rankness contributes to loss of trainability. And so based off of this story that I'm telling, our solution is quite simple. We're just going to regularize the largest singular values for our parameters. If we can control the largest one, maybe that will stabilize the training dynamics throughout the course of continual learning. So how are we going to do this? The idea is called spectral regularization, and it's called spectral regularization because the spectral norm of a matrix is the maximum singular value. And I'm going to show you how this regularizer works with just a single layer. So we have this neural network with a single layer with an activation function phi and parameters w and b. W is like the weight matrix that's multiplying x. B is a bias vector that gets added. And so we want the maximum single value of this parameter set to be approximately 1. And how we're going to do that is we're going to regularize the maximum singular value of w to be close to 1 and the maximum singular value of b to be close to 0. And we're going to do this through regularization, which means we're going to calculate the maximum single value of w and keep it close to 1 in terms of square distance, and then keep the maximum singular value of b close to 0, and again, in terms of square distance. Because this b is a vector, the maximum singular value is actually just the norm of that vector. And so what we're really doing is spectral regularization on the weight matrix and L2 regularization on the bias. And then for different layers, this is like a feed-forward layer. For like a convolutional layer or like a normalization layer, the idea might be slightly different, but the general concept is that for parameters multiplying on an input, we want that maximum singular value to be close to 1. And for things that are being added to it, like bias terms, we want that to be close to 0. So this is just for a single layer. Yes.
I'm just like want to understand like the intuition, like why do we need to regularize like a W to be close to 1, and for the W and then for the B is 0? Like why don't we just like keeping them all 0 or like all close to 1? Maybe I'm missing something. Yeah.
Right. So we want the singular value of this set of affine parameters to be close to 1. And one way to do that is you can think of the linear transformation as like b being concatenated into a vector of w. And then if you want to control the singular value of that concatenated matrix, it's actually the same as controlling the sum of the two. And so the reason I decided to do it like this is because think about the case where this maximum singular value for w is 0. That means actually that your weight matrix is a 0 matrix, which means you're not propagating information from the input to the output. But that's exactly what we would want from like a learning algorithm. Whereas if we had like a high norm on our bias term, that's not really giving us any information flow from like the input to the output. So if the maximum singular value of b is close to 0, it's not exactly 0, right? We still have some bias terms. They're just very small perturbations. So that's the intuition. There could be slightly different values. Like I'm thinking 1 here. Like I want the singular value to be close to 1. This actually is a heuristic choice. There's some work understanding what kind of spectral norms would we actually need in theory. But 1 seems to work well in practice.
I see. Thank you.
So this is for a single layer. In the case of multiple layers, it's pretty simple. We're just going to be doing spectral regularization on each layer. So we might have a neural network with depth L, and so we'll have like L sets of these parameters. And so we're just going to sum up the spectral regularizer on each layer. So for each of these layers, we're going to do what I showed on the previous slide. And then because it's a regularizer, how are we going to include it? We're just going to add to our unregularized objective, which I'm denoting by J theta, the regularizer, and with a regularization strength rho. So this is a hyperparameter that's needed for any type of regularization. And we're going to come back to this in our experiments to show how sensitive it is. So that's the main idea. There are a couple of things I want to point out that should make spectral regularization immediately appealing. First, unlike most approaches for maintaining trainability that I described at the beginning of this section, the initialization is not used explicitly. We motivate our understanding from the perspective of the initialization, but the actual regularizer itself doesn't really care that you are close or far from the initialization. It's not used explicitly. It's also less restrictive compared to, for example, L2 regularization. The reason being, in this case, is that what L2 regularization does is it's controlling the Frobenius norm of a matrix, and that's equivalent to regularizing all the singular values. Spectral regularization only regularizes the larger singular value. It doesn't touch any of the other ones. So at each iteration, L2 regularization is trying to constrain all the singular values, whereas at each iteration for spectral regularization, we're only controlling one. And then finally, you might be kind of concerned about maybe computational complexity, but because, again, we only care about the maximum singular value, that's quite easy to compute using power iteration. And so we have linear computational complexity. The last thing, which is a subtle point, is that the regularizer doesn't depend on data. Of course, L2 regularization also doesn't depend on data, but there's other ways of controlling the spectral norm. For example, there's spectral normalization, which is at inference time, when you are computing, let's say, your weight matrix times your input. What spectral normalization will do is it will calculate the spectral norm, the maximum singular value, and then divide the weight matrix by that. It turns out that the gradient dynamics for that network, a spectral normalized network, is actually data dependent. So the regularization strength, how much the gradient is influenced by the spectral normalization, depends on the data. And for continual learning, this is not very desirable. The data distribution is changing over time. So although we might have a good control over our spectral norm on one task, it might not be the case that it helps us on learning on the next task, because the regularizer is data dependent, whereas in our case, it's data independent. Okay, so again, returning to the example I showed before, let's just quickly verify the argument that I presented. So we saw before with unregularized training, we suffer from loss of trainability. And I was saying earlier that it would be ideal to at least maintain trainability in this task. And this is what we have with spectral regularization. This is with the regularization strength of 0.01, but I'll show in a couple slides that it's actually not very sensitive to this choice. And then I was also talking about the maximum singular value growing, which is problematic. And we can see that we're controlling the maximum singular value, although it deviates a little bit from initialization, is actually larger than 1. Again, because we're regularizing, it's not exactly going to be equal to 1. We have a trade-off between fitting the objective and fitting the regularizer. And what we see is that it hovers maybe around 2.5. And then finally, what's interesting is, although we don't explicitly control the minimum singular value, it's actually controlled too. The minimum singular value increases a little bit, but stays relatively constant throughout training. And what this translates to is, instead of a decreasing effective rank, we have an increasing effective rank with spectral regularization. Okay, so I showed you some experiments on relatively small scale studies of like random label MNIST. I'm going to present to you now a couple more results with larger networks and different data sets. So the overview of the experiments is I'm going to provide a comparative evaluation against a bunch of baselines. I'm going to be throwing a bunch of plots at you, but one at a time. I'll then talk about how regularization might impact the capacity of a neural network, the sensitivity to regularization strength. And then finally, I was talking completely throughout the talk about trainability. I'll present some early evidence to suggest that spectral regularization is also good for generalization. Okay, so the comparative evaluation is going to show you a bunch of plots, but I'm going to go through them one at a time. First, we have, in this case, random label SVHN2. So again, the non-stationarity might not seem very interesting. Memorizing random labels is not like a very realistic problem, but we just want to verify that what we saw on the smaller neural network on MNIST also happens on larger data sets with, in this case, a ResNet 18. And if you were to use an unregularized ResNet 18, after about 25 tasks, although you could fit maybe 80% of the observations as VHN2, over time, this decreases to about 50%. There's this idea of dormant neurons. So with ReLU activations, 1/2 of the activation is 0. As you accumulate these, as you train for a long period of time, some of these ReLU activations may stay zero on essentially all examples that it has seen. That's what's referred to as a dormant neuron. And what the idea behind dormant neuron recycling is just to reinitialize these dormant or dead neurons so that they are like alive again. And so dormant neuron recycling was motivated from the perspective of reinforcement learning, where normalization layers were not used very much. In this case, because we're doing like image classification, ResNet 18 has like batch norm layers. And this method redo, which is recycling dormant neurons, doesn't seem to be as effective. I will say though that on smaller neural networks that I've experimented with, it is quite effective, but on larger scale networks with batch normalization, it doesn't seem to be as effective. Then we can just do the simple thing of regularizing our parameters towards zero. This is L2 regularization, and it seems to do better than the unregularized case, but still you lose trainability compared to initialization. Then there's this idea called shrink and perturb, which is essentially L2 regularization towards zero plus noise. So it combines, in some sense, dormant neuron recycling in the sense that it adds noise and soft resets neurons, and also regularizes it. So it seems to be a little bit better than L2 regularization alone. And then there's L2 towards the initialization. As we argued before, the initialization is important. Maybe regularizing towards it could be beneficial. And although it seems to, at least within the first 5 to 10 tasks, be better than shrink and perturb and the other baselines, eventually it's around the same performance level for this problem. There's this other regularizer that we propose, Wasserstein regularizer, the details of which are not so important, but suffice to say that it is similar in regards to the other baselines. And then spectral regularization is, at least in this problem, the only method that A, doesn't suffer from loss of trainability, and B, quite interestingly, actually increases in its ability to train. So at initialization, we actually didn't have enough iterations in each task to reach 100% training accuracy. Again, this is a harder task than usual. SVHN2, without data randomization, would be able to get to 100% training accuracy, but because the labels are randomized, it's a much more difficult problem for the neural network to memorize all those random labels. But over time, after seeing enough tasks with spectral normalization, actually we improve our ability to train. This is one data set, SVHN2, but you see similar results on CFAR10 and CFAR100. Some of these lines are overlapping, but the consistent trend is without regularization, you suffer from loss of trainability. And in terms of the best performing baselines, spectral regularization is always at the top, but perhaps tied with other baselines, depending on the problem. So that's like the main result. But now we're going to be investigating a couple details surrounding the method, specifically the effect of the capacity of the neural network against regularization. So what we're going to do now is we're going to take the regularization strength that was most effective in sustaining trainability, and we're going to train for a long time on a single task. What we see is on a single task, the unregularized network, of course, does the best, right? There is no regularization, and so it can fit the random labels as best it can without caring about any other criterion. The other methods are not only optimizing the loss on this one task, but they also are regularized in some way. And what we see is that with spectral regularization, it's the least constrained compared to the other regularizers. So in the sense that it not only is good at continually training on a sequence of tasks, it is also quite performant in the sense that training on a single task, it's able to minimize the error the best. The other baselines are not too far behind, but still constrain the capacity of the neural network in terms of like the asymptotic ability for the neural network to fit the labels that it's given. Again, this is just a single task, but if you see if you rerun the same experiment on CFAR10 and CFAR100, you see a similar ranking where the unregularized neural network is, of course, the least constrained, whereas spectral regularization is always in second place. Now, an equally important part for continual learning is hyperparameter tuning. It's kind of a funny problem, right? When we're doing supervised learning and we want to just train on a single task, it does make sense to do hyperparameter tuning, right? We train for a little bit, we see how the performance is related to the hyperparameter we chose, then choose a new hyperparameter. But for continual learning, it doesn't really make sense because the idea is we deploy an algorithm and we never touch it again. We just let it run forever. That doesn't really make sense for hyperparameter tuning, right? Like, how can we tune a parameter if we don't really know how long we're going to be running this algorithm for, or what type of data it's going to encounter? And so insensitivity to regularization strength is particularly important. And I'm going to show you some results on random label MNIST, and the axes here are slightly different. On the x-axis, I'm showing regularization strength. So this is for different choices of like that row parameter, how strong is the regularizer? And then on the y-axis, I'm going to show the average end of task accuracy across 50 tasks. So I'm going to run a particular regularization strength with a particular regularizer 50 tasks, average all of those accuracies, and plot that here. So what we see is that for different regularization strengths, different methods perform differently, right? Like it seems like L2 towards 0, if you have too high of a regularization strength, it's not really learning anything, right? It's too close to 0 to learn anything interesting. Whereas, L2 towards initialization actually has like a region around here where it's relatively insensitive to the regularization strength. But what's interesting is for any choice of regularization strength, the spectral regularizer is the least sensitive and the most performant, in the sense that this curve dominates all the baselines. This is for 40 epochs, so you might ask the question, if we were to give the neural network more iterations per task, how much better can you use that capacity? And all the methods improve with more iterations, right? But this gap between the regularization strength choice and the performance given that regularizer doesn't go away. This is without layer norm, which layer norm is particularly helpful in improving trainability, especially for deeper networks. So let's try the same experiment with layer norm, and we see almost all the methods are better with layer norm, and yet the sensitivity to the regularization strength is still the least sensitive with spectral regularization. Whereas if you over-regularize on these other methods, you are particularly damaging the neural network's capacity, whereas without that, you aren't. And then finally, if we were to train for much longer with layer norm, we have almost this flat sensitivity with spectral regularization, whereas you can still over-regularize with these baselines. So in conclusion, in the context of sensitivity to regularization strength, spectral regularization is a particularly good choice. The last result I'll show is on generalization. And for this, I'll focus on CFAR 100 with ResNet 18. Here, the non-stationary is slightly different. With random labels, there's no sense of generalization because you can't learn anything from random labels. So in this case, what we're doing is we're permuting the inputs, the observations, the pixels. We're reordering the pixels at each task. And so that reordering is consistent across all the observations within a task. And so the task from the point of view of the convolutional neural network does change because the pixels are randomly ordered. But if it learns that ordering, then it can generalize to new examples. And so this is CFAR 100. There's 100 classes. And if you were to guess completely randomly, of course, you'd have a classification accuracy of 1%. As we train on some number on 100 tasks, what we find is without regularization, we're actually improving, but we aren't able to sustain that performance for generalization. We're actually decreasing a little bit from maybe 26% to 24%. Whereas with spectral regularization, it seems like it goes up and then stays relatively constant and above the other baselines. This is, again, consistent for different choices of data sets. So we can apply that same non-stationary to SVA Gen 2 or CFAR 10 or CFAR 100. And the trend is the same, where the generalization performance of the unregularized network can increase, but it can't be sustained. Whereas with spectral regularization, it can be not only sustained, but increased over the number of tasks. We ran also the same experiment with a vision transformer, and it's kind of surprising that the performance is quite different, but I suppose there is a good case being made that vision transformers are particularly good for generalization, or transformers are in particular good for generalization. And we see the same trend where the performance for the unregularized vision transformer can be increased, but it can't be sustained. Whereas with spectralization, not only can it be sustained, but it can be improved over time. In the context of CFAR 10, we see a couple more ties in the baselines at the top level, and for SVHN too. But for CFAR 100, we see this clean separation. So at least in some cases, it seems like spectralization is particularly good for improving generalization over the course of continual learning. So just some concluding thoughts. So the summary is that we discussed this idea of trainability. It's an optimization perspective on plasticity. We argued that singular values are can significantly influence trainability, and that spectralization is an effective approach to continual training in neural networks. It's insensitive to hyperparameters and shows some promising generalization results. Some future work is understanding the distinction between trainability and plasticity. Again, where plasticity is this idea of generalization, because the results that we have empirically and theoretically are mostly in trainability. It's a little bit easier to understand what it means to be continually trainable than continually learnable. But of course, learning is what we want to achieve in the end, not just training. I'm also particularly interested in developing more challenging continual learning problems, in the sense that the continual supervised learning problems can be somewhat toy, but also not very difficult. They're neither realistic nor challenging, whereas I would be interested in designing problems that actually kind of stress the ability of a learner to learn continually while adapting to changes over time, rather than just abruptly changing the task every, let's say, t iterations. And then finally, a bit closer to like low-hanging fruit is just applying spectralization to reinforcement learning, because the reinforcement learning problem has a lot of the aspects of a continual learning problem, and it has been previously demonstrated that methods for improving like loss of plasticity or improving plasticity have shown performance benefits in like training reinforcement learning agents in Atari. And so I'm particularly interested in applying spectralization in that setting. With that, just would like to thank my collaborators. So Saurabh is a PhD student at Stanford. Dale and Marlos are my supervisors at U of A. And Andras is a research scientist at Google DeepMind. This is the paper link and the QR code. Thanks.
Okay. Okay. So thank you for giving the talk. Yeah, I just have one question is that, so is it more difficult for like the learner to learn like a sudden change rather than the gradual change? Because like it's or maybe like I'm missing something, but like is because like it seems to me like intuitively, like let's say if you like you can frame the problems like shoppings, so there will be some hours that like there will be more like shoppers want to go to a shopping, so like the system can, but like that amount number can like maybe like gradually change, or there will be some signals that it will be changed, so I think the system can continually adapt to it. But let's say if like some surprising event has happened, then it's suddenly changed. So my intuition would be like, okay, so that example would be much more difficult to learn compared to the one that it's like gradually change and it's more signals that it will be changed. So like, and then you also mentioned that like in your example right now, it has a sign of like abrupt change, which is similar to like suddenly change, something like that. You just like switching the label without letting the learner to know like at what time you actually change. So is it safe to say that like if you can learn like even with this talk example of like suddenly change like that, can it also learn in like a more like gradually setting, or like it's not going to be equivalent, something like that?
Yeah, it's like an approximation to maybe what the real world is closer to, right? So it's also a little bit difficult to disentangle some things. So, for example, you may think that small changes are better, but sometimes the world does change abruptly, and being able to adapt to that is important. The other thing is, for example, you can not change all the labels, but some portion of the labels. And there's a result in a paper like Understanding Plasticity in Neural Networks that shows, isn't that? Yeah, I think so. That shows that if you randomize a portion of the labels, not like 100% of the labels, but let's say 10%, you pick 10% and you change those. As you vary this proportion from larger to smaller, this phenomenon happens later on. Like if you only like were to flip, let's say one image every t iterations, then yeah, it'll take many task changes for this problem to show up. But does that exactly capture what you mean by changing slowly? Maybe not, right? Because for any particular example, data is still changing abruptly. It's just not on all the examples you're changing. So in some sense, it's slower, but in other ways, it's not. The other thing I'll say is that you could imagine that the target changes slowly in the sense that doesn't really make sense for classification, right? Because we have one hot labels, but like in value-based reinforcement learning, where we're learning a regression target, the target might be changing from, let's say, a predicted value of 0 up to like 0, 0.1, 0.2, 0.3. And this we can control in the sense of like how slowly or quickly it's changing. So in that setting, I'm not exactly sure if there are any results for that. But I guess it depends on what you exactly mean by slowly changing. There's many different definitions.
I see. Yeah, I think Mark have a question. So
So, while we're on the topic of changing, um, does continual learning still cover when I change the number of labels? So for example, from your studies, what if I just started 1, 2, 3, 4, 5, train it on MNIST, and then I do another task when I train it to 6, and then I train it to 7, or I'm just changing the final layer of the softmax, but I'm still applying spectral norm to the other layers. Would that still be covered in continual learning, or is that just another paradigm itself?
Yeah, like in some sense, continual learning is a quite general framework, and we don't really know exactly what that framework is. It's not like we have something written down, like this is all of continual learning. It's kind of like right now a mishmash of like problems that we think fit that. Uh, could you restate maybe what exactly was the problem? So you have some set of MNIST images, you change
Yeah.
one at some point and then another at some other
Oh
point,
no.
or
I mean, I'm saying I'm adding labels, like I'm adding categories that I need to
yeah.
protect. That's what I'm continually learning.
Yeah. So that is a continual learning problem that people have been looking at, and I don't know if in my paper we look at that. I definitely didn't present results here. It's called class incremental continual learning. So yeah, you have some subset of labels, and then that grows. I do agree that that's an interesting problem, especially like let's say in the context of language. I think for image classification, it too is a little artificial. Like in what scenario do you know that you will encounter a particular label, but you have no examples for it right now? Like that seems like maybe that happens, but it seems a little unsatisfying still. Whereas in language, definitions of words change. I'm a bit more curious to apply some of these ideas also to NLP. I just don't have the background for that right now.
Okay, makes sense. Thank you.
Yeah. So there's like a class incremental continual learning, task incremental, and domain incremental. I don't think that even covers everything, but those are like the three terms that are commonly used in continual learning research. I remember trying to think, where does reinforcement learning fit in this? Because it does seem like a lot of reinforcement learning problems are at least sometimes continual learning. Like, if you can't find the optimal policy, then you're always going to be changing your value function. You're always going to be changing your policy, but it doesn't really fit into a box very nicely.
and do you think like part of the because like do you think part of the problems with like the continual learning like formulation it's coming from like we discretize like the time step, like because like it's just like maybe because I haven't watched like the thesis presentation from Chris, but I think Chris doing something with like the time step discretations, discretize something like that. I don't remember exactly, but it's just like give me some inspiration because like it sounds like because like it's not smoothly changing you still have like some like suddenly changed, even like how you define like sudden means, right? But if you really like discretize like the time step to be 1, 2, 3, 4, then if you look at that particular time step, then it's also like sudden change. But if you kind of like smooth things out a little bit, then like a time step, then maybe it's not suddenly change. I don't know. Yeah, just curious.
Yeah, that's a great point. You could put it another way, right? Like if I had the task ID in some sense, then it becomes not a continual learning problem. Then I can map task ID to random label assignment or something like that. Or you might say, I don't have the task ID, but I have a time step, and the time step could be mapped to a task ID and then turn it not to a continual learning problem. All those things are true, but they're difficult to make use of because time is always increasing. And like, how do you represent that? Maybe like on a frequency basis or something, but like it's still, it doesn't necessarily solve this problem. It may help alleviate it, but we don't necessarily have the tools to do that well. Like we have positional encodings, right, which are like a Fourier basis of like the relative positions of things. But because you already learned on something like many time steps ago, we don't have this relative embedding. We only have this ever-going time step, and being able to learn from that is difficult right now with like current like function approximators. But yeah, it's a really interesting idea and worth, I think, thinking more about.
I see. Yeah, thank you. Yeah, so is there anybody else have any other questions? Okay. Oh, yeah, Mark.
No, sorry, I just misclicked it. No, thank you for the talk, Alex.
Yeah.
Yeah.
Thank you.
Yeah. Thank you. Thank you, Alex.
Yeah. Thanks, everyone.
Okay. So thank you, everyone. So I will end the meeting here. Okay.
Okay, not sure if there is a bit tensor thing today, but if there is, doesn't look like it. Okay, well maybe there will be something interesting else happening, and I